Since Spider-Man's debut in 1962, the character has lost mentors, died, been cloned, rebooted, and retconned more times than I care to keep track of. But through it all, no matter the iteration of the character, Spider-Man always sticks to walls. Spidey just presses his hand against a surface and it holds, allowing him to run up the sides of buildings or walk on a person's ceiling. For over 60 years, that part of the spider powers has mostly stayed in the realm of superheroes. But there is a catch. Climbing up walls like the wall crawler might just be possible. The force behind Spider-Man's stickiness is something that's real. It's been known since 1930, when a physicist named Fritz London described it mathematically. It's the same force that's let spiders, or really anything that can climb up a wall, hold onto a vertical surface. And there's actual research being done and materials being designed that lets a 150-pound human being climb up a vertical glass wall. No radioactive spider required. Hello and welcome to the Chemist's Codex. My name is Peter and I like to find stories and the things that catch my interest because I believe those stories can teach us more about ourselves. And today's story starts with a question I'm betting Stan Lee never really thought about. What is Spider-Man actually sticking with? But before I get into the answer to that question, make sure to subscribe and hit that notification bell so you don't miss my future videos. And now that you've done that, let's talk about the real science behind Spider-Man's wall crawling. Although before I get into the science, I want you to think about what adhesion actually is. When you press your hand against a wall, your hand and the wall aren't actually touching, not in the way you think. Under a powerful enough microscope, every surface you've ever seen is more like a mountain range. Peaks and valleys of material, jagged and irregular, separated by empty space. When two surfaces come into contact, they don't merge, they just get really, really close. And close is where the chemistry begins. There are several ways you can get two surfaces to stick together. You could use an adhesive, a glue or resin that fills those microscopic valleys, hardens, and locks the surfaces together. Effective, but it tends to be permanent. Not useful when considering a superhero who needs to unstick and restick his fingers countless times per day without leaving residue on every building in Manhattan. His webbing already has that area covered. You could perhaps use suction, atmospheric pressure holding a cup-shaped surface against a smooth wall, but suction fails on rough surfaces and requires a rigid seal, not useful for flexible fingers on irregular bricks. You could use mechanical interlocking tiny hooks, catching irregularities in the surface, like Velcro, but that wouldn't work on smooth surfaces in the slightest. And herein lies the problem. Every adhesion mechanism that we tend to use has at least one failure condition when it comes to figuring out Spidey's sticky fingers. But there is still one more option. Intermolecular forces. Let's talk about electrons, because I will always find a reason to talk about electrons on this channel. Starting with the basics, electrons don't exist in the neat circular orbits that you might see in a high school chemistry diagram. That model, while it has its uses, is still a simplified version of reality. Electrons exist in clouds of probability, constantly shifting, constantly moving, never precisely located. And the thing about electron clouds, and more specifically the electrons within them, those electrons aren't always distributed symmetrically. At any given instant, the electron cloud around a molecule might be slightly denser on one side than the other. My go-to analogy for this is to think about a swarm of bees inside of a room. The bees might be completely spread out one moment, but then the next they might be congregated on one side, and then the next moment they might be up by the ceiling or crammed into a corner. You can think about electrons in a molecule behaving similarly, and it's purely statistical randomness, but for a brief instant, one side of a molecule carries a slight negative charge, and the other side carries a slight positive charge. We call this a temporary dipole, effectively turning the molecule in question into a tiny little magnet for a fraction of a nanosecond before the electrons shift again. But that momentary charge imbalance doesn't happen in isolation. The electron cloud of a neighboring molecule feels it. The negative side of the first molecule repels the neighboring electrons, pushing them toward the far side, which creates a corresponding dipole in the neighbor, which induces one in the next molecule, and the next molecule, and so on, cascading outward in a chain of momentary attraction. And the result is two completely neutral molecules carrying no permanent charge, forming a fleeting electrical attraction, purely because their electrons happen to be asymmetrical at the same moment. Fritz London described this mathematically in 1930, and as such we call them London dispersion forces. They are the weakest of the intermolecular forces, and let me give you some numbers to show how weak we're talking. A single nanoscale contact point generates an attractive force of about 10 nanonewtons. That's 10 billionths of a newton. In isolation, this force is so small that it doesn't even register as a concept. A single human hair exerts more gravitational pull on your scalp than one molecule exerts on its neighbor. So can this possibly produce superhero levels of adhesion? The answer is less about the strength of the force and more about the number of contact points. You can think of it like this. A single raindrop hits your windshield with hardly any force. but a strong enough storm can cause a landslide. The London dispersion force of a single molecule is a raindrop. Spider-Man's wall crawling is the rainstorm. And we can see how this works by taking a look at how spiders actually stick to walls in real life, because while they only have 8 legs, spiders are making contact in more than 8 places. Because a spider's leg is covered in structures called scopulae, and they look like tiny little brushes. And each of those brush fibers ends in a tiny little point, and each of those points makes contact with the surface the spider is climbing on. So it's more like thousands of points of contact at any given time, and when you add up the attractive London dispersion forces from each of those tiny little fibers, suddenly the spider has enough force to keep itself sticking to a wall. So if you think back to the first Spider-Man movie from 2002, back to the scene where Peter first climbs up a wall, right before he starts climbing, we see a magnified view of his thumb as tiny little fibers start to grow. Fibers that form the basis of how spiders actually do cling to walls and ceilings. But that does bring up a rather important question. Can this effect be scaled up? And the answer is yes, but again, there's a catch. Because geckos also cling to walls using this same principle. However, it's likely that a gecko is the largest animal that can climb up walls using this concept. For a human to do so, it's estimated that something like 40% of your body would need to be covered in scopulae to get the same effect. But scientists have turned to the toe pads of geckos to explore how a human might realistically climb straight up a wall, because those toe pads contain about 1 million microscopic hairs called setae. These are shaped more like a spatula rather than coming to a point like a spider's scopulae. But that's still a few billion contact points altogether, so naturally scientists thought we needed to try and build it ourselves. But before I get into how scientists are recreating a gecko's foot, I want to take a minute to look at why London dispersion forces are the only intermolecular force that makes this work. The molecular world doesn't run on just dispersion forces. There are, broadly speaking, 3 distinct forces stacked on top of each other in order of strength. Starting at the bottom, we have London dispersion forces. I've already explained these. They exist between every molecule in the universe, polar or nonpolar, large or small, simple or complex. Their strength scales with size, as larger molecules have larger electron clouds which can generate a stronger force. That's why octane, a large hydrocarbon with significantly more electrons than methane, is a liquid at room temperature while methane is a gas. But then taking a step up, we have dipole-dipole interactions, which involves taking a closer look at polar molecules, ones that have a permanently asymmetrical electron cloud. The result of some atoms in a molecule wanting to pull the electrons towards them and away from other atoms. This is a polar molecule, and polar molecules will orient themselves in crowds, the positive end of one attracted to the negative end of its neighbor, like a bunch of magnets aligning themselves with each other. This is a dipole-dipole interaction, more reliable, more ordered, and noticeably stronger than dispersion forces, but it only applies to polar molecules. Which then brings us to hydrogen bonding, and I want to be precise here, hydrogen bonding is not a chemical bond. It is a special, extremely strong dipole-dipole interaction, strong enough to warrant its own category. See, when hydrogen atoms bond directly to nitrogen, oxygen, or fluorine, 3 elements that are pretty good at pulling electrons away from other atoms, the electron cloud gets pulled so far away from hydrogen that it's basically left fully exposed. A bare proton carrying an intense partial positive charge, and that nearly naked proton is extraordinarily attracted to lone electron pairs on nitrogen, oxygen, or fluorine atoms on neighboring molecules. The result is a force far greater than a standard dipole-dipole interaction. This is why water is a liquid at room temperature instead of a gas. Every water molecule can form up to 4 simultaneous hydrogen bonds with its neighbors, and breaking those bonds requires quite a bit of energy, which is why water's boiling point is 100 degrees Celsius rather than what you might expect just based on its size. But let's go back to Spider-Man. Spidey's ability to stick to walls lives entirely within dispersion forces, the weakest intermolecular force, and while that might seem like a limitation, it's actually the whole concept. Dipole-dipole interactions and hydrogen bonding create persistent oriented attractions. Molecules attracted with those forces resist separation. They want to stay together. This is exactly what you don't want in a wall-crawling mechanism that needs to release on demand over and over without expending more energy than necessary. London dispersion forces are, by their very nature, temporary. Every single temporary dipole flickers on and off in nanoseconds. It is the only force on the molecular scale that could ever work for a wall-crawling superhero. Which then brings me back to the question of, can we do this at the human scale? In 2009, biologist Duncan Urshik and polymer scientist Al Crosby began collaboration at the University of Massachusetts Amherst. Funded by a grant from DARPA, their goal was to crack the problem of making an adhesive that functions like a gecko's toe pad, while also being usable at the human scale. The solution they found was counterintuitive enough that it almost doesn't make sense until you take a closer look at a gecko's foot. See, most commercial adhesives work because they're soft. They deform easily, flowing into the microscopic valleys of whatever surface it contacts. Soft means compliant, which means more contact points. And more contact points means stronger dispersion forces. So the obvious instinct when trying to mimic a gecko is to go softer, make more contact points. But Urshik and Crosby noticed that gecko anatomy doesn't actually fit that logic. Gecko toe pads contain stiff tendons which are able to distribute mechanical force across the entire surface. The consequence of this is that since the force is spread uniformly across the entire surface, there wouldn't be a disproportionate load triggering a failure in adhesion. Every contact point carries its share. Their solution, which they called Gexskin, incorporated a stiff woven fabric, think carbon fiber or Kevlar, as a backing to the soft adhesive pad. The fabric distributed the load while the soft layer made contact. An index card-sized piece of Gexskin is capable of holding 700 pounds on a smooth glass surface. It peels off cleanly with minimal energy costs, and it doesn't leave a residue. And then in 2014, mechanical engineers at Stanford published a paper in the Journal of the Royal Society Interface describing how they used a gecko-inspired adhesive to actually climb up a glass surface. This adhesive allowed Elliot Hawks, a graduate student leading the research, to climb up a glass wall using two handheld pads that held 24 of the adhesive tiles each. The pads were designed to apply an identical force to each adhesive tile, allowing contact to be maintained with the surface. And a critical part of this is a sawtooth-like geometry on the surface of the adhesive. When the pad first comes into contact with the surface, the tips of the pattern are what's contacting, which doesn't allow for strong dispersion forces. But as you flatten out the pattern, you get nearly continuous contact, which allows for incredibly strong dispersion forces, and you get adhesion. But then you can easily release the adhesive and have it ready to use again. And while this gecko-inspired adhesive can certainly be used to let a human climb up a wall like Spider-Man, there are so many more applications. Medical engineers are developing gecko-inspired surgical tapes that can function in wet, high-motion environments. The idea is that this tape can serve as a replacement for sutures or staples. The tape adjusts to the body's tissue and can be removed easily and painlessly. Or aerospace engineers are testing gecko-inspired docking mechanisms for spacecraft. Instead of mechanical fasteners that required powered actuation, a gecko-inspired system would just need contact and geometry. And yes, climbing suits are still actively being researched, but at this point it's not so much of a problem of how do we get something to stick, it's just a matter of engineering and design. All of this from the weakest intermolecular force. Thanks for watching. Full disclosure, this video was just an excuse for me to talk about intermolecular forces, but that's a pretty dry topic by itself, so I needed to come up with a framing device. And hey, I've been talking a lot about Spider-Man, so I figured why not use the character stickiness as a way to talk about intermolecular forces in a more interesting context. But now I want to hear from you. What do you think about the science behind Spider-Man's wall crawling? Leave a comment and let me know. And if you want more stories about the science that shapes our lives, make sure to subscribe and hit that notification bell so you don't miss my next video.